applying some pressure externally through the piston. Once you apply the pressure, what will happen to the volume? The volume will be get reduced. What is the first law of thermodynamics? So delta U is equal to Q plus W, and it can also be written as Q minus P external into delta V. The force which is applied on the piston, which is nothing but a pressure into area. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with a unit called Thermodynamics. In our last discussion, we have discussed about the types of thermodynamic processes, and also we have discussed about the change in the internal energy of the system, and also we have talked about the heat, how does it alter the internal energy of the system, and also very importantly we have studied about the first law of thermodynamics and the representations and the derivations we have understood. Today let us move on to the next topic of the unit by understanding the applications of first law of thermodynamics. Okay, and also we are going to understand the two more important concepts, that is enthalpy and heat capacity, and also we are going to learn one more important thing, that's the relationship between Cp and Cv for an ideal gas. We'll see what are the applications of first law of thermodynamics. So for this, I have considered a condition. Let us consider a cylinder which contains 1 mole of an ideal gas. So here I have considered a cylinder which is having 1 mole of an, which consists of what? 1 mole of ideal gas. Okay, ideal gas, and it has been fitted with frictionless piston. You can see that this is my cylinder having 1 mole of an ideal gas inside on it, and also we have closed the lid of this cylinder by using a lead along with a piston. Okay, this is a piston, and this piston is a frictionless piston. The total volume of the gas is considered to be Vi. So you can see that the volume inside this gas, it is considered to be Vi. So what does Vi stands for? Here the Vi stands for the initial volume of the ideal gas inside the cylinder. What is Vi? It is the initial volume of the gas inside the cylinder. Now, if you apply the pressure externally, now what you are doing? You are applying some pressure through the piston externally. What will happen to the volume? The volume will be get reduced, and it can be represented as Vf. What is Vf here? The final volume of the ideal gas after applying the pressure externally. Okay. So if the external pressure, that is Px, is greater than the P, the piston move inwards till the pressure inside the gas will be equal to the P external. Let the change in the volume of the gas can be achieved to the Vf. You can see that. So what happens here? In the first step, I have considered the cylinder. Inside the cylinder, we have taken out the 1 mole of an ideal gas. And also, we have enclosed the cylinder by using the piston. Initially, the volume of an ideal gas inside the cylinder is Vi. Now, I am applying some pressure externally through the piston. Once you apply the pressure, what will happen to the volume? The volume will be get reduced, so that the change in volume will be indicated by Vf. Because we all studied that this thermodynamics always deals with the state of the system from the initial state to the final state. So here, after applying the pressure, the initial volume of the gas is reduced to the final volume. So that is why I have indicated with the VI and VF. Now, the change in volume can also be written as delta V. So, it is also equal to the V final minus VI. Why it is VF minus VI? This is the volume of the gas at the final stage minus volume of the gas at the initial stage. So, the force which is applied on the piston, which is nothing but a pressure into area. Okay. This is, as we know, that force is equal to the pressure into area. Now, what will happen? You are doing the work onto the system. Correct? Now, you are doing the work onto the system. So, if W be the work done onto the system by the movement of the piston, then work done can also be written as W is equal to force into distance. What is the force now? Force is nothing but a P external into area of cross section. So, this is a total area, correct? No? Area of cross section. So, it is P external into A into L. L is nothing but a length. Okay, this is a length. Okay, L into A into L. So, now you can see that the area into area of cross section into length can also be written as change in volume, that is delta V. Why I have written with the minus delta V? Because I will explain why we have written the minus delta V in my next slide. Okay. Now, I have taken out this minus outside, minus P external into delta V, and we know that delta V, which is nothing but a change in volume from the initial state to the final state. So, minus P external, which is equal to V final minus VI. So, this is a work done at a final stage. Okay. So, this is how, by considering the first law of thermodynamics, we can understand the situation by considering a work done onto the system. Okay. So, this is how we can obtain this derivation, and it is an application of first law of thermodynamics. The negative sign of this expression is required to obtain the convention of sign for the W, which will be positives. So, here you can see that why I have introduced the minus delta V, because it is a delta V only. Why I have minus delta V? Because already we have understood that for the sign convention of the work done onto the system, it should be always positive. So, if I take the delta V as a negative, the change in volume can also be written as VF minus VI goes as a negative, and the negative will become positive. Due to this reason, I have considered the delta V as in the negative sign, because we always express the work done onto the system in a positive sign. In order to get a positive sign, I have indicated with the delta V with the negative sign. It will be multiplied with a one more negative sign to get a positive sign. So, it indicates that in case of the compression of the work is done onto the system, so the VF minus VI will become negative, and negative will be multiplied with a negative, you will get a positive. So, that this indicates that the work done onto the system will become positive. This is why, we have taken it as a negative way. So, hope you all understood. Next, we need to understand what is free expansion. Suppose if I consider an ideal gas, if you allow the gas to expand in an free vacuum where the pressure is 0, okay, such expansions are said to be free expansion. So, the expansion of the gas in a vacuum is said to be free expansion. So, where you are going to allow the gas to expand in a vacuum where the pressure is 0. Such expansions are said to be free expansion, and no work is done during the free expansion of an ideal gas whether the process is reversible or irreversible. Even though the pressure is 0, we cannot do any work for such kind of gases when the pressure is 0. So these are the main important applications of first law of thermodynamics, and also by looking at with the free expansion. Next, after understanding this, the applications of thermodynamics, first law of thermodynamics, we have understood that the first law of thermodynamics, it is indicated as delta U is equal to Q plus W. In the number of way, we can depict or we can rewrite this reaction based upon the types of processes. Already we have understood that there are different kinds of processes will be there. It may be adiabatic, isochoric, isobaric, reversible, irreversible, isothermal. So the different processes will be there. Based on the different kinds of processes, we can rewrite this first law of thermodynamics. We'll take up an example. Okay. So first, I'll go with an example. Let us substitute W as minus PVX into delta V in the first equation. So here, after understanding that work done which is equal to minus of external pressure which is applied into change in volume. So what you'll get to the first equation? So we know that the thermodynamic first law equations will be the change in internal energy will be equal to Q plus W, that is heat which is applied and work which is done. Now I'll consider work done as minus P external into delta V. What will happen to the first equation? Delta U will be equal to Q plus into minus P external into delta V. Okay. So this is the equation we get. Delta U is equal to Q minus P external into delta V. So this is a equation as we got by considering W as a, that is work done as a minus of P external into change in volume. Now I'll go with the isochoric processes. What will happen? We know that in the isochoric processes, we will take the volume as constant. If the volume is constant, what will happen to the equation? So if the volume is constant, so the P into delta V will be also become constant, so that delta U will be equal to Q. How we got? So we know that delta U is equal to Q minus P external into delta V. If it is an isochoric process, delta V will be equal to 0. So what will happen to the equation? So Q minus 0 P external into 0. Anything into 0, it will be 0. So delta U will be equal to Q. Okay. This is for isochoric processes. Next, I'll go for the isothermal and a free expansion of an ideal gas. For the isothermal process, of a free expansion of an ideal gas, I'll consider work done as 0 and P external which is also 0. If the work done is 0 and P external which is also 0, in the sense what will happen to the delta U? Delta U is also become 0, because we know that delta U which is equal to Q minus P external into delta V. If Q is 0 and P external which is also 0 into delta V, in the sense delta U will also equal to 0. Okay. This is for isothermal expansion. Next, for an adiabatic processes, we know that for adiabatic processes, the heat change will be equal to 0. So that is delta Q will be equal to 0. What happens to the delta U? Delta U will be equal to the work done of an adiabatic process. Like this, we can rewrite the first law of thermodynamics by considering with the different kinds of processes also. Now let us consider few more examples. Okay. For an isothermal irreversible reaction, if you take, suppose if you take isothermal irreversible process, we'll see what will happen to the first law of thermodynamics. What is the first law of thermodynamics? So delta U is equal to Q plus W, and it can also be written as Q minus P external into delta V. Okay. Now, for the isothermal irreversible process, delta U itself will become 0. So, what will happen? So, Q into P external into delta V, or you can rewrite this reaction as delta U is equal to Q plus W, which is delta U is 0 in the sense. So, you can write Q is equal to minus W. Okay. Q is equal to minus W, and what will happen to this equation? If delta U is equal to 0 in the sense, Q is equal to, you can write Q is equal to V F minus V I, that is change in volume into P external. Okay, this is as we got from the isothermal irreversible processes. Now I'll go for the isothermal reversible processes, where again delta U will become 0. What will happen? We know that Q will become a minus W. So which is equal to, it is an forward reversible reaction where you are converting that reaction to come back to the original state, where you are applying some pressure for that. Correct? No? So Q is equal to minus W, which is equal to nRT ln Vf divided by Vi. In order to remove this ln, we need to multiply with the 2.303 nRT into log of Vf divided by Vi. Now, if you wanted to express in terms of pressure, this is in terms of volume. If you wanted to express the work done in terms of pressure also, we can rewrite it as W is equal to minus 2.303 into nRT into log of P1 divided by P2. This is for isothermal reversible processes. We can rewrite the first law of thermodynamics. Next we have enthalpy. So next we are going to understand about the enthalpy. We'll see what is the enthalpy and why it has been used. Enthalpy of a system can be defined as the total heat content of the system. What is enthalpy? It is a total heat content of the system, and it is measured as a sum of the internal energy and a product of its pressure and its volume, and it is always denoted by H. So it can be denoted as what? So the enthalpy is nothing but the total heat content of the system, which is always equal to the internal energy of a system plus the product of pressure and volume. Okay. So this is for enthalpy. The enthalpy will depends upon the substance and also on the state of the system. So how much of the heat quantity which is present in the system can be mainly depends upon the two things. Whether the system which is present with which state, and also with the nature of the substance which is present in it. Okay. Hence, it is a state function and also it is an extensive property. Why the enthalpy is known as an extensive property of the state function? Because it is depending upon the state of the system and also about the quantity of the substance. If the property which is depends upon the quantity of that substances, such properties are said to be extensive property. Here, our enthalpy is depends upon the quantity of the substance which is present inside the system. Hence, it is an extensive property. And since we know that this is an example for state function because it is depending upon the state of the system. Okay, that is why it is an state function and an extensive property. Now, the change in enthalpy can also be written as delta H, which is equal to delta U plus P delta V. We know that for an ideal gas, PV is equal to nRT. If I consider for an ideal gas, volume of the N will be always equal to 1. So that PV nRT can also be written as, I have taken out the P delta V, which is equal to delta Ng into RT. What does this delta Ng stands for? It is nothing but a number of moles of the gas product minus number of moles of the gaseous reactant. So delta Ng, which is nothing but a number of moles of the gas product minus number of moles of the reactant. So this is known as what? The delta Ng. It is nothing but a number of moles of the gas product minus number of moles of the gaseous reactant. So that I can rewrite this equation as delta H, which is equal to delta U plus delta Ng into RT. Why delta Ng into RT? Because we have considered delta PV as delta Ng into RT. This is how the change in enthalpy can also be written. So hope you all understood with the enthalpy and how it is known as extensive property, why it is known as a state function, how does we can rewrite the change in enthalpy also we have understood. Next we have the few things to note while dealing with the enthalpy. Okay. So for the solid and liquid, the term, the pressure and volumes are become negligible. Correct now? If you are dealing with the solids and liquids, the term, the pressure and volumes are negligible. Whereas when we are talking with the gaseous substances, the pressure and volumes are matters more than with the solids and liquids. So that H will be equal to U. What is the H? It is nothing but the amount of heat content. That is the enthalpy will be equal to internal energy U. In a chemical reaction, the change in enthalpy can also be written as delta H, which is equal to H product minus H reactant. Why is it so? This is only for the chemical reaction, because we know that in a chemical reaction always the reactant is giving rise to product. So the change in heat of that system can also be written as delta H is equal to H product minus H reactant. Enthalpy of an element is assumed to be 0 for the standard state, and delta H, which is equal to Qp, that is the heat absorbed by the system at a constant temperature. Suppose if you say that delta H is negative, it is an exothermic process. If you are saying that delta H is negative and delta H as a positive, it is an exothermic process where heat is liberated, and it is endothermic process. Okay. If delta H is negative, obviously it is an exothermic process where during that chemical reaction lot of heat is liberated. Whereas delta H is positive only when it is an endothermic process where it is the heat is get absorbed from the surrounding. Okay. At a constant volume, if you consider, what will happen to the change in enthalpy? The change in enthalpy will be equal to delta H will be equal to delta U, which is equal to Q into V. So this is how the few things we need to know regarding to the enthalpy. Next we have heat capacity. Okay, the increase of temperature is proportional to the heat transfer to the system. If you increase the temperature, what will happen to the heat capacity of the system? It is also get increased, and it can also written as Q is directly proportional to the change in temperature. So Q is nothing but a heat, how much you are supplying to the system, and delta T is nothing but a change in temperature. In order to remove this proportionality constant, I'll write Q is equal to C into delta T, and Q is nothing but a heat supplied onto the system, delta T is a change in temperature, and this C stands for heat capacity. Okay, and there are two types of heat capacity which is there. One is molar heat capacity and the one is specific heat capacity. We'll see what is a molar heat capacity first, and it can be written as Cm. Okay, it is defined as the quantity of the heat needed to raise the temperature at 1 mole of a substance by the 1 degree Celsius. So what does it stands for? It stands for the quantity of the heat needed to raise the temperature of the 1 mole of the substance by 1 degree raise in temperature. Whereas specific heat capacity can define that it is defined as the quantity of the heat required to raise the temperature of 1 unit mass of the substance by 1 degree Celsius. So it talks about the 1 unit mass of the substance, whereas a molar heat capacity talks about the 1 mole of the substance. So the differences you can find it out with the specific heat as well as with the molar heat. When it is said to be molar heat, 1 mole of the substance we consider. When we are talking specifically, we say it is 1 unit mass of the substance. Okay, the temperature can be raised by 1 degree raise in temperature, so that we can rewrite that Q is equal to C into delta T. Next, we have the relationship between Cp and Cv for an ideal gas, and this derivation is very important for the examination point of view, and it can be asked for 3 marks. Okay, we'll see how to derive this equation. Okay, so just now we have understood that the C stand for heat capacity. What is that Cp and Cv then? We'll see now. At constant volume, the heat capacity can be written as Cv. At constant pressure, the heat capacity can be written as Cp. So what is Cv and Cp now? This is a heat capacity at a constant volume. This is a heat capacity at a constant pressure. Now we have understood? Yes. Now we can rewrite the entire equation of the specific heat. What is the specific heat? Equation Q is equal to C into delta. So this is a specific heat capacity equation as we have understood, and also it is a heat capacity equation. Now I'll consider the heat which is applied onto the system or supplied onto the system at a constant volume, so that QV is equal to CV into delta V, which is nothing but a change in internal energy. At the same time, I'll consider the heat which is supplied onto the system at constant pressure, so that QP is equal to Cp into delta T, which is nothing but a change in enthalpy. Now you know we are talking about the ideal gas, correct? No, we know that ideal gas is equal to PV is equal to nRT. So how we can rewrite that? Delta H, which is equal to delta U plus delta into PV. So delta U plus delta PV can also be written as what? RT by considering 1 mole. So PV will be equal to RT. So I can rewrite the PV as RT. Now this RT is a constant. So delta U plus R into delta T, and you can write this equation as delta H, which is equal to delta U plus R delta T. So this is a change in enthalpy of the system. Now by substituting the value of delta H and delta U to the above equation, we can rewrite that as, so what is the delta U and delta H? Delta U is nothing but a Cv into delta T, whereas delta H, which is equal to Cp into delta T. When you apply for that, you know, so what is the delta H, which is equal to Cp into delta T, which is equal to Cv into delta T into R delta T. Now delta T will be get cancelled out. What is the remaining? Cp is equal to Cv plus R. I'll take out the Cv outside. Cp minus Cv, which is equal to R. This is a relationship between the ideal gas. That is the relationship between the Cp and Cv with an ideal gas. R stand for ideal gas. Okay. This is how you know the heat capacity of a system or heat capacity of the particular system at constant pressure and a constant volume can be taken, and we can create a relationship between the heat capacity at a constant pressure as well as at a constant volume, okay, which is equal to the ideal gas equation. So hope you all understood with this derivation. Definitely this derivation can be asked for 3 marks. Okay. So in the next session, we are going to discuss with the measurement of the delta U and delta H. I'll come up with the next unit. Till that, take care, be safe. Thank you.